Hello YouTube. In this video I'll be covering the Weierstrass approximation theorem. So if you've ever used a calculator in your life, say in like the SAT, AP Calculus, whatever, maybe Desmos, you've probably had to evaluate something like sine of 37, and you get some like weird decimal like 0.601815. By the way, this is in degrees, and then the list of decimals goes on and on and on. You might be wondering how the heck the calculator comes up with this number. When I was a student doing AP Calculus, I certainly was wondering that. And I used to think, and don't make fun of me, that the calculator had just like a stored list of values, like sine of 0.0 is equal to 0, sine of 0.001 is equal to something, and the list goes on to infinity, right? So you even have something for sine of 1000, and who knows what's beyond that. Now, as you can probably guess, that's not how a calculator works. And in this video, I'll be covering how not how calculators work, but the sort of mathematical underpinnings as to why calculators work. And yeah, the solution to this that engineers and mathematicians have come up with is a lot more interesting than just a stored table. A calculator wouldn't be able to have all that. It wouldn't have the memory to store all this. Okay, well, I guess we can move on to the actual statement or theorem that I'm trying to cover in this video. Huzzah! Here's the statement of the Weierstrass approximation theorem. So let epsilon be a positive constant. Now, for any continuous function, f mapping the closed bounded interval a to b to the real numbers r, there exists a polynomial p of x such that the maximum error between f of x and our polynomial is bounded by epsilon. Okay, so let me just kind of give some calculus-like intuition on what a continuous function is. So you have two real numbers a to b. You take the interval, so all the numbers in between inclusive, so we have a and b part of it as part of our set. And then say this is like x and y, so we have a 2D coordinate grid. Now we can define a continuous function so that every single number in between a and b has a corresponding value in y, right? So we can draw this curve here, and it's continuous. So we have no holes, no jumps, no discontinuities, no funny shenanigans, just a continuous function, honest to goodness. Okay, so what this theorem is saying is that you can create a polynomial p of x that can approximate our function f arbitrarily well. It does not matter what f is. As long as it's continuous, you can create a polynomial that can approximate it arbitrarily well. Okay, and what is a polynomial in this case? Well, in this video we're covering algebraic polynomials, but in maybe a future video we can cover trigonometric polynomials, which is like using sinusoids, sine and cosine. And okay, what is an algebraic polynomial? It sounds fancy, but it's just like a function like x squared plus x plus 5. And the most general form is actually the summation from n equals 0 to big N, where big N is a finite number and hopefully pretty big, of a of n, where a of n is a coefficient, times x to the n. So, for example, for some set of a of n, this could look like 1 plus 0.2x plus 5x squared. And you can choose all the coefficients in between, and you get like 4x to the big N minus 1 minus 0.2x to the big N. Okay, and generally, as you let big N become larger, you can create better and better approximations for f of x. Remember, this is your p of x. Now, the theorem is saying that there exists combinations of a of n and big N such that it can approximate an arbitrary function as well as you want. So what would that look like in this case? Well, we don't exactly know what f of x is, but we know it's continuous. And say we could set epsilon to be a small number, 10 to the negative 6th. Well, what this theorem is saying is that you can define a polynomial in this interval such that it's pretty dang close to your f of x. In fact, the maximum that the p of x will ever stray from f of x is actually bounded above by epsilon equals 10 to the negative 6th. So For example, say that this point over here is the point where our p of x strays off course from f of x the most. We can say that the error at this point is at most 10 to the negative 6. It can never be more than that. All right, pretty cool, pretty cool. How's this useful to the scenario that I was talking about in the beginning? Well, let me explain after I finish erasing all this stuff. Okay, so if you may recall, we have sine of 37 degrees. That's like approximately equal to 0.601815. Perfect. So what? Well, you think about your standard TI 84, which you've probably encountered if you've touched AP Calculus before. It doesn't really know what sine of x is. Oh, and in case you were wondering, our f of x that we're choosing is equal to sine of x, right? And sine of x is continuous, in case you didn't know. And say we could set and this is degrees, by the way. So we could set a to b, the interval to be like, I don't know, 0 to 100 degrees, for example. Okay, so our calculator doesn't know what sine of x is. The most the calculator can do is multiply, add, subtract, divide. That's pretty much all it can do. And so when you feed it a request like sine of 37 degrees, it doesn't have like an operator that tells you what 37 degrees maps to in the real numbers. All it can do is add, subtract, divide, multiply really quickly, right? So what it does is it has a polynomial that approximates sine of x really, really, really well. In fact, correct me if I'm wrong, this is up to machine precision. So say epsilon is really, oh, I didn't spell that right, really small. Which would also probably imply that n is our degree of the polynomial is really big. Then, yeah, we can just construct a polynomial. So we'll call it p of x is equal to n equals 0, big N, a of n, x to the n. And this polynomial is so freaking good that for this really small epsilon, we get that f of x minus p of x is pretty much always less than epsilon. No, it just is less than epsilon, the error for all x in the interval, a to b. And in this case, we're setting our interval to be 0 to 100. But our interval can be whatever. Doesn't matter as long as these are both real numbers and it's b is greater than a. Okay, and one more note that might be interesting. So let me just erase this. First of all, you've probably heard of something called Taylor series. So the Taylor series is just a set of polynomials that are standard for approximating stuff like sine of x, e to the x, cosine of x. And the Taylor polynomial for sine of x is actually x divided by 1 minus factorial, divided by 1 factorial minus x cubed divided by 3 factorial plus x to the 5th power divided by 5 factorial. And you get the pattern. It alternates in sign, and then you increase the exponent by 2, increase the factorial by 2 as well. Right? Now, this theorem, it tells you that there exists a polynomial that can approximate f of x arbitrarily well, but it doesn't really tell you how to find such a polynomial. But there are methods for this, and in which case there are something called Taylor series, and that's a pretty standard way. It uses nth degree derivatives. So for sine of x, that would be a polynomial that looks like this. And you'll eventually get to some polynomial. Since a calculator cannot handle infinity, you'll eventually get to a point where you'll have like a plus or minus, I don't know which, x to the big N divided by n factorial, big N factorial. And how big you set this limit is going to directly affect how good your approximation is of sine of x. This is approximately. In fact, in calculus, you'll probably learn, I don't know if you'll prove, but actually sine of x is equivalent to the Taylor series, which I'll just denote by this, but all the way to infinity. So you have a polynomial that goes off to, there's infinite number of terms. Technically not a polynomial, but you get the idea, right? The limit as you go to infinity approximates it infinitely well. Okay, yeah, that pretty much covers everything I wanted to cover. I would have really liked to cover trigonometric polynomials because that would explain how, for example, engineers are able to, or computers are able to compress like a 3-minute, like if you sing for like 3 minutes, the computer will be able to record that and kind of compress it instead of recording every little bit of information from your voice. But I won't have time for that, so thank you for watching and I'll see you next time.